Right, we're covering lecture 2 today, and lecture 2 is the second part of chapter 2 because we didn't finish chapter 2 last week. If you want to recap on what was happening last week, then obviously you can go onto YouTube and watch the video of the lectures that I put up there. So this is where we got to last week. We've covered up damped oscillation. We talked about the free oscillation. So what happens when you have a damped system and you excite it, or sorry, you don't excite it, you move it away from equilibrium position, you let go and let it oscillate. What happens then? This week we're going to move on to the forced oscillation. So what happens when you actually excite it? In this case we're going to excite it with a sinusoid and watch what happens. And then we're going to talk about the alternative forms, okay? Because often, if you look up physics books or engineering books, dynamics books, different people talk about these equations in similar terms, but not always the same terms, okay? And so what we're going to do is we're going to talk about some of these alternative forms, some of the new different variables you may come across, and some of the different terms that are used in this book as well. And then after we've covered that, we'll go through and do some examples, some of which will use these alternative forms to show you how sometimes it could be easier to use those alternative forms than not. And there's one question I'm going to go through where I'll do it both ways and you can see how they match up together. So forced damped oscillation we can represent like this, okay? We have a mass, a spring. Spring is at equilibrium position when x is 0. Okay, and we can extend the mass by distance x in the x direction. Okay, and we have a damper this time with a damping constant c. So that's going to oppose the motion. It's going to oppose any velocity. Remember, and then we've got a force being applied, F of t. Now, if we take Newton's second law for the system. Sum of all the forces equals mass times acceleration. Well, here we've got a spring force, which is at minus because it's always opposing motion, so it's in the minus direction. We've got a damper that opposes motion, so that's a minus cx dot. Okay, and then we've also got this sinusoidal exciting force, which I've called F0 cosine omega t. Now remember, omega here, omega without any subscript is the force that I'm imposing upon the system. Okay, it's not the natural frequency of the system. So if natural frequency of the system, say, is 5 Hertz, and I'm imposing 20 Hertz, then that's 20 is what omega is there. Okay, it's not the 5. F0 is some amplitude, and you can see it's just a cosine signal of some description. Starting at t equals 0, cosine of 0 is 1, so it starts at 1 times F0. Okay, so there's Newton's second law, and we can rearrange that and make those substitutions that we made before, where gamma is c upon m, and omega naught squared is k upon m, because remember omega naught, natural frequency, is square root of k upon m. And we're also going to move to the complex plane, okay? As we discovered last week, sometimes using the complex plane makes life easier, so that's what we're going to do. And so and because we've moved to the complex plane, we've replaced x with z. So we have z double dot plus gamma z dot plus omega naught squared times by z equals our sinusoidal forcing function. But of course, because it's a sinusoid, it's oscillation, we can replace cosine omega t with the complex form of that. And then when we go back to find x at the end, we just replace that ej omega t, we find the real part of that, and we end up with the real function. But we're going to do something else when we do this. The trial function. Last week I talked about trial functions, and you may be thinking, well, why did I choose that instead of something else? Well, often the trial function will take the form of your forcing function. Okay, if the forcing function is a sine or cosine, we might take the trial function to be a sine or a cosine, which is what we did last week. Here I've got an exponential, so my trial function is an exponential. And in chapter 3, when we talk about finding solutions to different forcing functions, not just sinusoids, we're looking at other sorts of functions, I'll talk a bit more about which trial function we need to try. Okay. Here we've got an exponential, so my trial function is also an exponential. Okay. I've got my amplitude of my trial function that we're going to find. Okay, omega, that's my driving frequency. And this delta term is there to accommodate any sort of phase lag we have, and I'll talk about that in a minute. Because basically there is a situation in with this example where your driving force can be in one direction, but the thing's actually moving in the other direction. And that's accommodated by this phase lag. Because you'll be at if that was the case, you'd be at 180 degrees out of phase. And so this term would actually equal pi, as it happens. But we'll talk about that in a minute. Now remember, at this stage in the course, we're looking just at the steady state solution as time goes to infinity. If I took that system and I started shaking it, to start with, it wouldn't like it because I'd be oscillating it at a frequency that's not its preferred frequency. Okay? And there'd be all sorts of transients going on, and we'll discuss them in the coming weeks. But after a little while, that thing will give up and will start oscillating with me, okay, at the frequency that I'm imposing upon that system. And that's the solution we're going to find today. We're not going to worry about the transient bit. Okay, and with a damped system, we learnt last week, with a free oscillating damped system, okay, the damping will kill out the oscillation and the thing will end up becoming stationary. We saw that. Okay, well that's exactly what happens. Is as I start oscillating it at the frequency that I want, to start with I'm fighting with its natural frequency. Okay, but after a while that natural oscillation is going to die away because it's damped, and it's just going to be me oscillating it at the frequency that I choose. Right, so we've got that trial function, and we're going to substitute that trial function into the complex equation of motion. Notice there's a small typo there. Into the complex equation of motion. So we take that trial function, we take the second derivative of it and the first derivative of it, and we then insert it into our trial function. Okay? Are we all clear where I got the second and first derivative terms from? Yeah? We go back to the trial function. First derivative, we get an omega that comes out the front. Okay, and a j comes out the front. So we have j omega times z. And if we take the derivative of that, okay, then obviously another j omega comes out. Now j times j is minus 1, and omega times omega is omega squared. So that's where we get the omega squared minus omega squared term, and then gamma j omega from, okay? We've taken a out the front, and we've taken the e j omega t minus delta out of the back, okay? And then there's our forcing function, which we've not changed. Now what I'm going to do is I'm going to multiply both sides by e, well the e j omega t cancels, and I'm going to multiply both sides by e j delta, okay? And this makes sense if I just write it on the board. What am I doing? Well, why am I doing this? Well, this side, on the left-hand side, we've got e j omega t minus delta. Okay, well that equals e j omega t times by e to the minus j delta. Okay. Now that one cancels because it's on both sides, so that disappears. And if I multiply this by e j delta, okay, obviously that's going to be e to the power of 0, which equals 1. Because you have minus j delta plus j delta equals 0, so that equals 1. So I can do that. And because I've multiplied both sides of the equation by that, I end up with this term on this side. The e j delta term on that side. And in the complex plane, we can separate this out. We know what that is. Exponential from last week, Euler's relationship. E to the power of j delta must equal cosine delta plus j sine delta. Okay, we covered that last week. So I'm just putting that back into its sort of component form with a real part and an imaginary part. So now we've got an equation. And this equation has real parts, and this equation has real parts. and this equation's got complex parts, and this equation's got complex parts. And then what you need to do to solve that equation is you need to equate the complex parts and the imaginary parts separately, okay? Yeah, if you've got apples here and apples here, well that's fine, we can deal with it in apples, and here we've got oranges, okay? But you can't deal with apples and oranges together, you have to separate them out, okay? And so, we can separate it out, we end up with two equations. So if we take the real parts, we've got a minus omega squared plus omega naught squared, okay, well that's times by a, must equal f naught upon m times by cosine of delta. Okay, that's all the real parts in one equation. Then we do the same thing with all the imaginary parts. We've got gamma j omega times by a equals f naught upon m times j sine delta. Now obviously the j's will cancel, we don't need to worry about them. There's a j on both sides, let's get rid of them, so we're just dealing with those terms there. We have two equations and two unknowns. What are the unknowns? What don't we know? We don't know what A is. Okay, we know what omega is because that's the force, that's the frequency I'm oscillating at. We know omega naught if we know the characteristics of the system, but we don't know what the amplitude is. Okay. The other thing we don't know is we don't know what the phase lag is. As I said, there are some circumstances where there will be a phase lag. The thing will not oscillate in the same direction that I'm moving it, or I'm applying the force. So we need to accommodate for that. Two equations, two unknowns, but we can solve it. Great. Let's do so. This is the equation for A. The way you can get to this, if you wanted to do it on yourself, do it on your own, is you square both sides, square both equations even. You end up with a sine squared and a cosine squared. And we know that sine squared plus cosine squared equals 1. And so you can combine those two equations, doing so, and you end up with a term for A. Okay? F naught upon m divided by the square root of the difference in the squares of the frequencies squared plus omega times by gamma squared. Quite a complicated equation, I admit, but we're going to talk about it in a bit and it'll make a bit clearer sense. And later on in this lecture, when we talk about alternative forms, I'll show this, but in an alternative form that's a bit simpler to comprehend. What about delta? Well, we saw that in the previous slide with the two equations, we had a sine and a cosine. You divide sine by cosine, you get tangent, okay? And obviously you get what's up here, and obviously if you take the inverse tangent of omega gamma divided by omega naught squared minus omega squared, you get a value for delta. So there's our two unknowns. We know everything about the system. Let's dive a bit deeper. We can now return to the real world, and to do so we change z back into x. Well, that was the equation that we had, if you remember, but now we know what A is and we know what delta is. And so there's our solution. Great, wonderful. We know everything about the system, we can find the solution. If I give you a frequency and you know characteristics of the system like the mass and the spring stiffness, and I give you a force, then you can solve everything about the system that we need to know. What's the amplitude at a certain frequency and all sort of malarkey. This time, A and delta, we looked in previous cases where these were adjustable. You can choose whatever you want. Here they're completely not adjustable. They are defined explicitly by these two equations. Okay, you cannot adjust them. They're defined by those equations. And they're defined by characteristics of the system, so things like omega naught, so K and M. And they're defined by characteristics of that applied force, F naught, and the frequency at which I'm applying that force. Okay? So there we go. So that's how we define A and delta. And so we know the whole solution to this system. Let's look at A in a bit more detail. Now without looking at the equation in too much detail, let's use our intuition. What happens when omega is close to 0? Think about the system. If I'm applying a frequency that's you know, 0.000001 hertz. Okay, so very, very slow. Okay, what is the amplitude of that motion going to be? Well, the amplitude of that motion is basically just going to accommodate it's going to bring the spring system into equilibrium. The thing is so slow that damping has no effect. Okay, and all that force is doing is equalising with the spring force. And so you end up with the F equals kx type equation, or x in this case is the amplitude. And so you can say the amplitude is just going to be F naught upon k. If I write that on the board, I'll just do it in this corner. Ka, because that's the amplitude, well A is obviously just going to be F naught upon k, yeah? The thing's just equalising the force that I'm applying. Now if we look at this in this case, if omega without the subscript is 0, okay, you end up with an omega naught squared on the bottom, or it's in fact just an omega naught squared on the bottom. F naught upon m omega naught squared, I'll show in a second, but you can rearrange that to be F naught upon k. Before I do that, let's just look at this equation once more. What's good about this equation? Well, F naught is in the numerator. That's a good thing. You can imagine if you're applying a big force, a large force, the amplitude's going to be bigger. The other thing that's good is that I notice the gamma term is in the denominator. Well, that's good because you can imagine if there's a lot of damping, which would increase gamma, then obviously I've got less amplitude. So like I said, what about different values of omega? As omega approaches 0, we said that it's going to be the spring force. Okay, F naught upon k is the amplitude. And that makes sense to us intuitively. And if you look at the equation, like I said, you get F naught upon m omega naught squared. Okay. Now omega naught squared we know is k upon m, but it's on the denominator, so it's m upon k. The m's cancel, you end up with F naught upon k. And that term, F naught upon k, is known as the static displacement. Okay, static displacement. F naught upon k. And that's always the case with these systems. If somebody says, what's the static displacement of that system? Well, it's F naught upon k. And it's the same when we looked at undamped systems. It doesn't have any damping term in there, so it doesn't matter whether you're damped or not undamped. It's always the same. F naught upon k is the static displacement. What about for delta? Well, again, let's think about it intuitively. If omega is 0, so I'm not applying it with any great force, any great frequency, okay, it's, my period could be 100 years or whatever, I'm applying a force, but it's going to take 100 years for it to do an oscillation. Well, the omega term there drops to virtually 0, and notice that that's in the numerator. And so we end up with inverse tangent of 0, and inverse tangent of 0 is 0. And that makes sense to us intuitively. If you think about it, if my frequency is so slow, okay, the thing's not going to have any trouble keeping up with my movements, is it? There's going to be no lag between me applying a force and it moving. No lag at all. So delta is going to be 0 in that case. Like I said, you can prove it from the equation. If you put omega naught to be 0, then you get omega in the numerator, you get some value in the denominator, so you get tangent of inverse tangent of 0, or inverse tangent of 0, if you know tangent is 0. Okay, so that makes sense. What about if we drive the system at its resonant frequency? If we drive the system at its resonant frequency. Well, let's use the equation this time, let's not think about it intuitively. If we took that equation for A, and we set omega to be omega naught, let's go back to that equation for A. Have I got, yeah. If we set omega to be equal to omega naught, then obviously that term disappears. Yeah? Omega naught squared minus omega naught squared, 0, okay? That term would be omega naught times by gamma, obviously all squared, and so you put that, that's the case when omega goes to 0. So you end up with that omega naught times by gamma, that term was squared, but obviously it's the square root of that, so it stays the same. So you end up with this equation, okay? You can show this to be true. If you know that omega naught is root k upon m, you can do some manipulation and you can find out this to be true. And so you can see that the amplitude at the resonant frequency is equal to this term, omega naught divided by gamma, times by the static displacement. F naught upon k was the static displacement when omega is 0. Well, when you're at omega naught, you get some amplitude that's greater than the static displacement by this amount, omega naught divided by gamma. And what we do is we introduce this quality factor or magnification factor, depending on who you listen to. It's called both of those terms. And that Q happens to equal omega naught divided by gamma. And so we now know that if omega approaches omega naught, the resonant frequency, our amplitude is going to be the static displacement multiplied by that quality factor. Why is it called a quality factor? Well, if Q is related to the natural frequency and obviously the damping, if you've got a very high Q factor, you can think of it as having a very high quality oscillator, so the damping is low. Q being high, damping's low. Damping's on the denominator, okay? If Q is very low, then you can think of it as a poor quality oscillator. Damping must therefore be high, okay? What about the last case, where the driving frequency approaches infinity? So I'm shaking it really, really, really fast. Yeah? If I'm shaking it so fast, do you think the thing has even time to respond? The answer is no. Okay? If you think about it, if you're shaking something so fast, it's not actually going to respond to that movement. And so your amplitude actually drops down to 0, approaches 0. And that makes sense. If you stick infinity in the denominator, anything divided by infinity is 0, okay? It's tiny. It's somewhat less obvious what delta does in the last two cases, but we can just take that the following applies. As omega approaches the resonant frequency, our delta term goes from 0 to pi upon 2, okay? Pi upon 2 being 90 degrees. And as it approaches infinity, my delta term goes to pi. Pi being 180 degrees. And so in that case, if I go above my natural frequency in terms of the excitation force, my phase lag is going to increase, and it will increase to such a point where I end up with the thing being completely out of phase with my applied force. I'm applying a force this way, it's actually moving that way. Doesn't make sense, but that's the case. And what we can do is we can now plot what A and omega does for what A and delta does for various values of omega, and you end up with some plots that look like this, okay? Here we've got amplitude versus frequency. You can see as frequency approaches 0, we've got a value of f naught upon k. As you increase the frequency that you're driving the system at, you reach a point where you hit resonant frequency, and you can see the amplitude is increased by such a distance to get to this point, depending on your value of gamma. If gamma is small, you go up here. If gamma is big, you come down. If you remember, recall back to when we were looking at the free forced oscillation. You remember at this point, it went up to infinity. Well, gamma has just brought that limit down from infinity to some point over here. Then, obviously, as you go past the resonant frequency, the amplitude dies down and eventually will hit 0. This is why if you excite something at resonance, it can be pretty destructive. Okay? Imagine you're doing a plane, got the jet engine hanging off the wing, there's obviously something mounting that jet engine, and the jet engine obviously is an oscillatory thing, it rotates. And if you happen to be rotating it at the same frequency at which the stiffness of that mounting bracket, okay, you're going to have the amplitude of that oscillation is going to increase massively because you're exciting at that. And so either you don't want to operate it at that, you want to do it in this region or this region, but don't operate it in the middle. If you are aiming for this region, you want to get through there as quickly as possible because there will be some damping, and it can probably deal with a small time of it being at a peak amplitude, but not long. And you can see with the delta, At 0 frequency, we've got 0 in terms of phase lag. As you get up to the omega naught, we're 90 degrees out of phase. Okay, and then as you approach infinity, that phase will approach 180 degrees, or pi, which is 180 degrees out of phase. And again, that relates quite closely to what we saw with the free oscillation. You saw, remember, with the free, we had the amplitude went up to infinity, then came up from minus infinity to 0. Well, minus infinity means it's 180 degrees out of phase, yeah? If it's got a minus sign. And that's exactly what happens here. It's the same thing, except for it's represented in a slightly different manner. We've got a phase and an amplitude. Now, the eagle-eyed among you would have noticed that at high damping, so this end, you can see that the maximum point of this curve is slowly moving away from this point here. You can see that for this one, the maximum point is over here. Okay, it doesn't always occur at the omega naught. It depends on the value of your damping. Okay, you can see that the maximum point is over here for this line, but it's virtually on omega naught for that one. Well, if you have high damping, then omega max, which is our maximum, is the frequency at which you reach that maximum point, is defined by this, okay, where there's that Q term again, and the amplitude is defined by this. I'm not going to go through the derivations of it, but that's the case. But the thing is that don't worry too much about it, because you need a really, really, really low value of Q for it to make any significant difference. Q is is equal to 5 here, so it's very underdamped. Okay, so you've got massive oscillations, not much damping at all. Okay, and if you work out omega and omega naught, you can see that we're 0.99 of omega naught. So it's 1% lower. Not much really in the grand scheme of things. And then again, if you take the maximum amplitude at that point and you divide it by the static amplitude, you can see, if you remember, maximum was Q times the static displacement, or here, Q is 5, here we get 5.03, so 0.6% higher than Q, okay? So it's minuscule. And that's with Q equals 5, so a really underdamped system. Okay? And most systems, like I said, we can assume it's more or less the same. Don't worry too much about it. It's here for completeness. Right, so that's force damped systems. Okay, and basically we went through some derivation and we found two equations, or we found the solution. The solution for when, let's go back, keep going, there we are. The solution is x of t, x is a function of time, is a cosine omega t minus delta, where a is that complicated function and delta is this less complicated function. Okay? Okay. Now, some of you may have noticed in the introductory chapter I said something about an equation sheet, equation formula, okay, a formula sheet. There will be one. It's not in the notes. I didn't put it in the notes. And that's because the version I had ready for when the notes were going wasn't up to date. But there will be some additions to what goes up, and obviously the equation sheet I'll upload to Blackboard in due course, and you'll then have it. But some equations, like these ones, will be on there, so you don't need to worry too much about remembering them. Okay, let's move to alternative forms. Okay. Now, I know some of you will have come across this term in previous modules, damping ratio, because you would have covered it last year. And that's defined as C divided by the C at which you get critical damping. Damping ratio is the damping of the system that you know about divided by the damping that would give you critical damping, C. And we know from the previous sections of the notes that critical damping occurs when omega naught squared minus gamma squared upon 4 equals 0. So you can solve it, you get omega equal gamma upon 2. And if you do that substitution back, knowing that gamma is C upon m and omega is root k upon m, it can be shown that Cc is 2 times root m times by k. And so we can stick that into that equation at the top, and you get damping ratio is C divided by 2 root mk, okay? So if you know the damping of your system, you can find the damping ratio by dividing it by the critical damping value, and that's equal to 2 root mk. And so if you know the mass and you know the stiffness and you know your damping, you can find your damping ratio. Why is damping ratio useful? Well, it's quite nice. If you've got a damping ratio of equal to 1, then obviously C and Cc are the same, so you're critical damping. If you've got a damping ratio of less than 1, 0.5, 0.2, whatever, then you know you're in an underdamped system, and so if you excite your system, it's going to oscillate. There's going to be an oscillation. And we saw last week, if you're in an overdamped system where your damping is greater than your critical damping, then obviously you've got a overdamped system, and so the thing's not going to oscillate. It's just going to fall down to equilibrium position with no oscillations. That's useful. What about the relationship between this gamma term and the damping ratio? Well, we can go through and define it. If we find out what C is in terms of damping ratio and critical damping, we can find out that C equals 2 zeta root mk, or 2 times the damping ratio, that's the zeta in Greek, root mk. And if you stick that into gamma, which we know is C upon m, then you can see that gamma is 2 zeta omega naught. Just go through the motions, applying your knowledge, and you get 2 zeta omega naught. Have you covered Laplace in control yet? Yeah? No? Not yet? S? What sort of terms? Perhaps not. I shan't confuse you if you haven't. But you'll see this term in the characteristic equation. When you're solving those differential equations, you'll see that term when you're dealing with a mass spring damper system. And what about this Q value? We can again put that in terms of zeta, omega naught divided by gamma. We know that gamma is that, so we stick that in here. Omega naughts cancel, we get 1 over 2 times zeta. And you can see, we said that a low Q is a poor quality oscillator, so damping must be high, okay? Well, here our damping ratio is in the denominator, so we get a, if damping's high, this value is big, we get a low value for Q. If damping is low, this value is small, this must be big, that turns into big, okay? Right, so that's damping ratio. Damped natural frequency, omega d, we came across this. That was the equation that we looked at. Omega d, the damped natural frequency is omega naught squared minus gamma squared upon 4. And so obviously we can square root it to get omega d. Substituting in equation 1, what's equation 1? Equation 1 is the one we came across beforehand. Apologies about that. Equation 1 is gamma equals 2 zeta omega naught. Gamma equals 2 zeta omega naught. That's the equation we're substituting in here. So we stuck that in here, we get 4 zeta squared omega naught squared. Obviously the 4's will cancel out, and so we end up with this. Omega naught squared minus zeta squared omega naught squared. The omega naught squared can come out, so if we square root it, we end up with this equation here. So that's the other way of finding the damped natural frequency if you know your damping ratio, okay? You just plug it into this equation instead of finding out what gamma is and all that sort of malarkey. Damping ratio, natural frequency, you can find your damped natural frequency. And you can see that if the damping ratio is tiny, i.e. very low damping, then these two things are going to be more or less equal to each other because this value will be close to 1. Okay? Amplitude ratio. Well, we talked a little bit about this. Remember, static displacement is F0 upon K. Now if you divide f0 upon k by the amplitude that you're actually at, you get a ratio, because it means that, and that ratio basically is normalised about the static displacement. If you take amplitude, that is the static displacement, you've got f0 upon k times by k upon f0 equals 1, okay? So at static displacement you've got an amplitude ratio of 1 to 1. Obviously as your amplitude goes up or goes down, you stick that in there, you get a value of greater than 1 or less than 1, and obviously that will give you the amplitude ratio of that particular amplitude if you plug it into this equation. So m is amplitude ratio, it's referenced to the static load, it's normalised about the static load. And the same can happen with frequency ratio. We normalise it about omega naught. If you've got an omega that's less than omega naught, then obviously you've got a value of less than 1. When you're at the resonant frequency, you've got a frequency ratio of 1, and then you've got a frequency ratio greater than 1, and omega must be greater than omega naught. Okay? So it's just a matter of normalising these terms. You'll sometimes come across m and r, or if somebody says, what's the amplitude ratio? Well, you know that we're talking about this, not the actual amplitude. Okay? It can help when you're describing terms. And so we can plot those two graphs that you just saw in terms of m and r. And you can see that at 0 frequency we've got an amplitude ratio of 1, normalised about the static displacement. Okay? At resonant frequency we've got an amplitude ratio of, in this case, up to 5. And then as you go towards infinity frequency ratio, then you end up getting the amplitude ratio reducing to 0, which is what we expect. And here delta is the same, you've got between 0 and pi, okay? But at 1 is where you cross over the natural frequency. Okay, does that make sense? Yeah? There's some nods. Yeah, okay, that's good. Now, knowing those various different forms, things like damping ratio, amplitude ratio, frequency ratio, we can redefine some of those equations that we saw in terms of those terms. And sometimes, like I said, and we'll come across this in one of the examples I'm going to do, that it helps often when to use these alternative forms. And so let's go through some. Underdamped system. Okay, so this is a free damping. So we're not driving it. We had this equation. But we didn't have it in this form. We had a gamma upon 2 term, okay, where the zeta is. For an overdamped system, again, replacing that gamma upon 2 term, we can replace them with zetas, okay, and you end up with that form. And then for a critically damped system, again, there was a gamma upon 2, there was a gamma term in here, I believe, and that's obviously gone to omega naught. I believe that's the case. Let's see. Yes, there was a gamma upon 2 term in here for the old-fashioned version. For force damped systems, this is what we've just looked at earlier on. We had an equation for A that was quite complicated. Well, nicely, if you do a bit of manipulation, you end up with that, which is much nicer and easier to deal with. Suddenly gamma's disappeared, you've now got a damping ratio, and instead of the omegas and omega naughts, you've got your frequency ratio. Okay, R. If you want to deal in omegas and omega naughts, then you can use this version. It's up to you. Depends what's easier. But the difference is the gamma's gone, but the damping ratio is there. And for the phase angle, you can apply similar logic. We had a relatively complicated equation. In terms of omega and omega naughts and zetas, you can have this form. And if you replace the omega by omega naught by R, which is what we did earlier, then you have that form, which is, again, arguably nicer and easier to deal with. It depends what you've been given in the question, to be honest. Remember, when the amplitude is equal to omega naught, when your frequency is equal to omega naught, the amplitude we said was q times the static displacement. Well, we can replace q with 1 over 2 zeta, 2 times the damping ratio, and you get the same thing, because q equals 1 over 2 zeta. So again, a nicer alternative form. 248. That one.
Yeah, how come can change to 1 minus r squared if r equals
Yeah, indeed, you're right. There is a missing 2 there. That should be omega naught squared. Apologies about that. Thank you for pointing it out. Thank you for pointing out the error. Great. Top marks for you, you're paying attention. We're almost there. Then you can have a break. And remember I talked about the peak frequency and maximum amplitude, okay? Where omega maximum, or the maximum value for maximum frequency at which you get the maximum amplitude, in terms of zetas you can replace those terms with these ones. Okay. And then lastly, we were lastly on the last slide, but this time it really is lastly, general solutions. Now, again, you may have come across an alternative form for an equation that looks a bit like this, okay? A cosine omega t plus phi. That can be written like this. Get rid of the phase and we end up with cosine and sines in the same thing, okay? They're the same thing. A and A1 and A2 are obviously different from each other, okay? But it's exactly the same equation. How do we know that? Well, let's think about trigonometry. Going back to, is that GCSE maths or A-level maths? I don't know. I didn't do either. You end up with this difference identity, sum and difference identity. Cosine of u plus v is cosine u, cosine v minus sine u, sine v. Okay? Now before we had omega t plus phi as the u and the v terms, okay? So obviously you can separate that out into that difference formula. A cosine omega t plus phi must be equal A cosine omega t cosine phi minus sine omega t sine phi. Now if we set A1 to be cosine phi, and we set A2 to be minus sine phi, then you can say that, so that's what I've just said, you can say therefore that A cosine omega t plus phi is A1 cosine omega t and A2 sine omega t. So if you know A and you know phi, you could either use this equation, or you could find these two terms and then use this equation. Doesn't matter. Either works. And sometimes you'll see me write this equation in this form, and sometimes you'll see me write it in this form. But like I said, as long as you're aware of the fact that they're the same thing, it doesn't matter. And so, obviously you can put that form into the undamped response. Xt, this is undamped, okay, so there's no e exponential term, undamped response. A cosine omega t plus phi is A1 cosine omega t plus A2 cosine omega naught t, where A1 is A cosine phi and A2 is minus A sine phi. Free damp response, so there's our damping term, the exponential, decaying exponential. Okay, again, you can separate out the omega dt plus alpha, A cosine alpha minus sine alpha, and you end up with that term there. And then lastly for that, well you can obviously do the same thing for the forced damp response as well, because we had a omega t minus delta, so there will be a plus sign, a minus sign in there. Okay, initial conditions. What do we mean by initial conditions? Well, what we mean by initial conditions is the conditions when time is 0. Okay, when t equals 0, what's the situation? Those are the conditions that we're setting out initially. And by knowing the initial conditions, you can often work out these unknown quantities. In this case, we can work out what A is and we can work out what phi is. Okay, and I've called them x naught you can either write x naught with in brackets, or an x subscript naught means initial displacement, and then obviously x dot with naught in parentheses is equal to x dot naught, okay, and that's the initial velocity. And by knowing those two things, you can work out some of these initial conditions. Now we can also write those as solutions in terms of x and x naught, or x naught and x dot naught. Here we've worked out that x naught is a cosine phi. Well, we know that a cosine phi is a1. And we know that minus a omega naught sine phi, well, we can rearrange that by dividing x dot naught by omega naught. We end up getting minus a sine phi, which we know is a2. And so you can rewrite that equation, that solution, in terms of this. So if you've been given a problem and you say you've been given all the initial conditions such that it's at rest at time equals 0, but you have some value of x naught, then obviously you can rewrite the equation like that. If you've been given an initial velocity and you're saying you don't know where it is, then obviously you can rewrite the equation as well. It doesn't matter. But it's quite a nice, easy solution, and I'll show you this in a minute as well. For free damp response, a bit more complicated than an equation. Okay, because you've got that exponential. If you stick t as 0 for the displacement, you get a e to the 0, which is 1, okay, or a, cosine omega times 0 plus alpha, well omega times 0 is obviously 0, so you have cosine of alpha. X naught is a cosine alpha. And then for the derivative, obviously you've got to find the first derivative of that response with respect to time, and that's why it gets a bit complicated. Because we have an exponential in terms of time and the cosine term in terms of time, we have to use the product rule to take the derivative of this with respect to time. This is why we've ended up with a cosine term and a sine term in the same equation. The cosine term has a zeta omega minus zeta omega term in front of it, which comes from the exponential, and then the sine term has an omega d term, which comes from taking the derivative of the cosine to give us minus omega d sine omega dt plus alpha. When we set time to be 0, the exponential becomes e to the power of 0, which is 1, and the omega dt terms in the sine and the cosine become 0, so we end up with cosine of alpha and sine of alpha. And so the velocity when time is 0 ends up being a times by the quantity minus zeta omega naught times by cosine of alpha minus omega d times by sine of alpha. From the equation for displacement, we know that x naught equals a cosine alpha. So we can rewrite the velocity equation at t equals 0 as minus zeta omega naught x naught minus a omega d sine of alpha. And we can rearrange that solving for minus sine alpha, giving us x dot naught minus omega zeta x naught over omega d. So we now have terms for a cosine of alpha and minus a sine of alpha, which are our a1 and a2 terms in the solution that we found earlier. That solution is shown at the top of this slide. So we have our a1 equals x naught and a2 equals x dot naught plus zeta omega naught x naught over omega d. We can then insert these terms for a1 and a2 into that general solution, and we get the solution in terms of the initial conditions. We shall be using this solution in the example that I'll be doing after the break. But if you know the initial velocity and the initial displacement, you can insert them in for x dot naught and x naught respectively to find the general solution.